Swayam Prabha. Digital India. Educated India.
Welcome back, my dear friends. A very good morning, good afternoon, good evening to all of you who are taking this TQM2 course under the NPTEL MOOC. And I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, this is the 15th lecture for the TQM2 lecture series of the course. And as you know that each week we have 5 classes, and after each week we have one assignment. So, we are at the last lecture for the 3rd week, which is the 15th one. Now, if you remember that we were doing, after going into details about the ANOVA concept, that how you use the concept of analysis of variance, try to find out the sum of the squares for the error, sum of the squares for the treatment. I am using the word treatment in a very general sense, it will basically be the experiment we are doing. And then you will try to find out the total sum of the errors, how we will try to differentiate using the concept of design of experiments, and then you will consider the concept of hypothesis testing. And if you remember, we did go into details about the hypothesis testing concepts in the first 7 lectures. I would say almost till the end of the 7th lecture, after which we started the concept of design of experiments in a very preliminary way. Then we also considered under the ANOVA so called models, if the means are same, if the tau values, which is the difference in the average of the averages with respect to the treatment means. Again I am using the word treatment for that example. If you remember the etching, depending on the overall wattages or the energy levels of 160, 180, 200, 220. We also saw that how the degrees of freedom would change a minus 1 depending when you are considering the inter or the intra level of sum of the squares. We also consider a very important concept was where the variances of the samples of the populations for each etching was same, and that means variance was not changing, not dependent on time. That was a very important concept. I will be repeating it time and again, please bear with me. Then we also considered that if you are trying to compare, so the compares would be for the balanced model, non-balanced model, and the random factor models, so on and so forth. And we took the example of the etching problem time and again to highlight all the different facets and different ways of trying to tackle the problem. Then we went into, though not in that depth like the etching problem, into the aluminum smelting problem, and also showed the different concepts of the models. And then we came into the concept of the factor models. Factor models, if you remember in the 14th lecture, which was the second last lecture of the 3rd week, we considered that if there were 2 levels of influence, one was A plus, A minus, and with respect to that you had another factor which was B plus, B minus being the levels, and how those the relationship between the factors could be either increasing in a linear way or they would be decreasing. That means there is inverse proportions, and we drew diagrams or graphs to show that how they can be at least justified in a very nice manner. And though the relevance of the quantile paths was more discussed in the ANOVA models, but it will be utilized in the factor models also later on. So, why this was important? Because if you remember the 4 distributions we considered, the Z distribution, the T distribution, which were only related to considering something with the mean, and Z was being used when all the information about the standard deviation of the population was known, t distribution with a certain degrees of freedom, which I did mention time and again, would be used for the case when the standard deviation of the population was not known. Then if you go into the second moment of the variances comparison, we took the chi-square with the change in the degrees of freedom depending on what the problem formulation was. Then we went to the F distribution. Then we also considered the Bartlett's test, the Tukey's capital T statistic, and considered those examples again for the same two detailed example about the etching part and the aluminum smelting part. So, to again come back to the factorial models, we will continue discussing those, and as I said that as you do the assignment, small problems, these things of the concept would become much more clearer to you, and for all the queries we as a group from the MTTL, the instructor, which is me, and my TAs would be there to answer all your queries to the best of our knowledge and our ability. And for any other queries, obviously I would request time and again, please read the book. I know it is a little bit more quantitative, a little bit on the higher side, but please trust me, that is one of the best books which you could have followed both in the TQM1, the Montague one, which was basically related to statistical quality control, and then this one basically being from the design of experience area. So, design of experience book is also there by Montgomery, but you can basically go through the initial framework of the ideas from the statistical quality control and then switch over to the higher level book, which is the design of experiments. Now, continuing the discussion which we ended in the 14th lecture. So, the parameters we want to find out. So, if you go back, so there was basically a very simple linear model. Now, the linear model would be fx would be coming on a standalone basis from the factors, and they would be so called interrelationship of the factors. So, say for example, the factors as x1 and x2. So, the overall effect would be coming on a standalone basis from x1, on a standalone basis from x2, as well as the combination of x1 and x2, and you can formulate models accordingly. If there are 3, so obviously it will be x1, x2, x3, and the combinations of 2 taken at a time for the 3, and then the last one would be the combination of all the 3 taken at one go. So, the parameter estimates in this regression model turn out to be related to the effect estimates. So, what are the effects and how you can find the estimates. For the experiment shown in the previous lecture, which is the 14th one, we found and the main effects of A and B. If you remember, A and B are the factors. So, we mentioned them as A plus the higher level of factor, A minus and B plus, B minus corresponding higher and lower level for the second factor. So, continuing the reading as written in the slide, we found the main effects of A and B to be A being 21. If you remember, that was the so called average effects, and for B was 11. Now, the estimates of beta 1 and beta 2. So, if you remember, beta 1 was the so called rate of change of, considered in a very simple way, the rate of change of the dependent factor or dependent effect being dictated by 1 unit change of x1, and beta 2 would be basically the rate of change of the dependent factor per rate of change of x2, which is the second factor, and you can find out the factors rate correspondingly. So, the estimates of beta 1 and beta 2 are 1/2 of the value of the corresponding main effects. So, obviously, you will try to find out the average. So, now rather than beta 1 and beta 2, they would be mentioned as beta 1 hat and beta 2 hat corresponding to the estimates which you find out from the sample, which you will think is the best estimate or the best statistic which you are trying to utilize from the sample to find out the parameter values in the population. So, beta 1 hat comes out to be 10.5 or 10.5, and beta 2 comes out to be 5.5. So, the interaction effect which is given in the figure 5.1. So, the figures which I refer one can basically simply refer to the book which I have been referring time and again. So, the effect of A and B comes out to be 1. So, the value of the interaction of the coefficient, the regression model, considering the joint effect comes out to be 0.5. So the parameters of beta naught is basically the so called intercept. If you consider the concept of very simple linear line which we have done in very simple algebra, very simple trigonometry or very simple mathematics in class 10. So we have y is equal to mx plus c. So m is the rate of change of y with effect to 1 unit change in x, and c was basically the intercept. So that beta naught value is the intercept, which is calculated as, obviously it will be beta hat. So I may be mentioning beta hat or may not be mentioning beta hat, but the crux of the discussion is that this is the best estimate which you are getting from the sample. So beta hat not is in the suffix, comes out to be 35.15. Now once this is solved, when you write out the model, this is what we have. I will try highlight it and again come back to whatever I said about few minutes back. So this is the effect which I have. So it's not highlighting, so I'll just mark it here. So this y hat, now you will be thinking why it is y hat. Now when you are trying to basically mention a model, so the model would basically have a part which is so called deterministic part plus the error term. Now if you remember the error term which we did consider in the ANOVA model, and we will be considering time and again in different type of models, we will consider it to have a mean value of 0 and a variance to be either 1 or sigma square. But the fact still remains that the sigma square value, which is the error's variance, remains constant, such that the effect of the errors are not there to be considered. Important point, I will keep repeating it time and again. So therefore the fitted regression model comes out to be, now on the left hand side of the equality sign is y hat. So you may be thinking why it's y hat, because y hat is basically the predicted value. So that will be equal to beta naught, which is beta naught hat is 35.5 plus 10.5, which is beta 1 hat into x1. So you plug in the value of x1, you will get the second term, that is 10.5 multiplied by x1 value at that point of time where you want to find out the y hat. The beta 2 value would be 5.5 into x2 hat, and the third term would basically be beta suffix 1 and 2, which is the joint effect, multiplied by x1 and x2. So again it is beta 1 2 suffix hat, plus in the actual model there was an error. So this error terms, once you find out, would basically be the difference of y actually at that point of time minus the y hat value which you have found out. So if you basically take a roundabout way of trying to analyze the error terms, so for each and every value, different values of x1, x2 and x1 and 2, which is the suffix value. So all these combinations which you take for the first reading, second reading, third reading, fourth reading, so on and so forth, you will have different values of y hats. So it will be y hat suffix 1, y hat suffix 2, y hat suffix 3. If you find out the differences of the corresponding y1 minus y1 hat, you will have the error term 1, which is the first value of the error. If you find out the difference of y suffix 2 minus y suffix 2 hat, you will basically have the error 2, and so on and so forth. So if you want to double check the actual assumption which we have mentioned time and again, that the error term has an average value of 0. So adding up all the error terms in the long term and for many readings would definitely come out to be 0, because the average value is 0. So hence the value of error is not there, because you are trying to find out the estimated value. The parameter estimates obtained in the manner for the factorial design with all factors are 2 levels, and they turn out to be least square estimates, in the sense that we are trying to find out conceptually. Let me I am not going to digress, but I am going to go into a little bit different mode and trying to give you a philosophical discussion, is that when you find out the errors, so technically what you want to achieve, let us step back and think, you want to achieve the errors such that the variance of the errors are minimized. So if the variance of the errors are to be minimized, which means technically that you are trying to basically find out the variances of the difference between the actual value and the estimated value as low as possible. So obviously cannot be made 0, it is to be as low as possible, corresponding to the fact that you find out the best estimates of beta naught hat, beta 1 hat, beta 2 hat and beta 1 2 hat. So, once you find out, so what you are trying to do is that you are trying to put those values in such a way that the error terms would have the minimum variances. Obviously, there would be other concepts of trying to find out the minimum variance also, but we would not consider those in our discussions for this TQM course. For the problem solving, I will just give you an example as and when they come up, in order to make you understand that there would be different ways, other ways also trying to analyze the errors, such that they may not give you the actual theoretical concept, but practically they would basically make things much clearer to you. So, the interaction coefficient, which is beta hat 1 2 is 0.5. So, is very small relative to the main effect. So, obviously you can drop it, in the sense that if you combine the effects of x1 and x2, their rate of change or the effect on the value of y is only half of that value, this is 0.5. So, figure 5.1, again referring to the book, represents the graphical representation of the model. In figure 5.5a, we have a plot of the value of y values generated by the various combinations of x1 and x2. So, you take different combinations of x1 and x2 and try to plot them. This 3-dimensional graph is called the response surface graph. Now, you may be thinking why it is 3 combinations, because you have y and you want to basically find out the effect of y on 3 combinations, number 1 on x1, number 2 on x2 and number 3 is x1 suffix 1 and 2, that means combined effect of them. So, the figure 5.b shows the contour lines of the constant response of y in the x1 x2 plane, because x1 and x2, when you draw the plane, they would combine the combinations of x1 and x2 also, which is x suffix 1 2. Notice that because the response surface is a plane, the counter plots contains parallel straight lines. So, now is the diagram which I did mention. I will try to come to that discussions once again. So, if you consider figure 5.5a, you have, if you notice, on the y axis, which is where I am pointing my left hand, this is the y value, and on the x axis and the z axis, because there is no z. So, what we are trying to do is that plot x2 and plot x1. So, as is a linear line, hence the the contour of the surface would basically be a plane. So, in the 2-dimension case, if there was only x1 and no x2 or x suffix 1 and 2 was there, it would be a straight line in 2 dimension. In the higher dimension, it would be a plane, and in the higher, still higher dimensions, it would be a hyperplane, which we basically utilize that in the concept of theoretical concepts, to be clear. Now, when you are looking at the plots of x1 and x2, the relationship between them, obviously you are, if you can notice figure 5.5a, and if you eliminate y, what you are looking is that you are looking from the top, like if just to digress. So, in mechanical design or civil engineering design, we use the trying to draw on any object, we use the plan, the front view and the side view. So, in the plan and the front view and the side view, when you consider them to be constant, in the sense that you are looking parallelly along the diagram, such that there is no variations in the values of y. So, if you plot them, they would basically be slanted lines with a tan value of negative values. So, which means that if you plot them, those lines as parallel as I am pointing my this pointer. So, these are the values which gives you a relationship between x1 and x2, depending on what are the on the values of x1 and x2 correspondingly. So, if you plot, say for example x1, consider this value as 1, and if you go along this diagonal line, so you will basically be able to plot for different values of x2 and x1 what are the combination values you will take amongst them, such that you get the overall effect in the y value. So, y value is not being shown here, because they are just a plane which you have not considered, because you are considering this diagram here in a 2-dimensional plane. And obviously, in a 3-dimensional plane and higher up, you can basically visualize how they are basically being plotted. Now, another thing, in the model we have considered that y is equal to beta naught plus beta 1 into x1 plus beta 2 into x2 plus beta 1 2 into x1 2 plus the error term. So, for the timing, considering the error term is not there, so what we get is basically the y hat value. Now, if you extend that model to a higher dimension, say for example x1, x2, x3, and you are basically trying to find out the relationship of y based on the effect of on an individual basis on x1, on x2, on x3, and again as I mentioned, the combinations of 2 taken at a time, which is x1 into and x2, x1 and x3, and x2 and x3, and the last one basically being the combinations of x1, x2, x3 taken all together at a time. So, if you plot that, it will be a hyperplane, but in the case as I mentioned, but in case if it is a nonlinear one, so obviously the plane which I drew or which was shown on in figure 5.5a would no longer be a plane, but it will be a curved surface, and you can find it accordingly how the relationship varies. This is just for a thought process, and you can basically visualize how would the diagrams would look like. The advantage of factorial design can be easily illustrated. Suppose that we have two factors a and b, each are at two levels. So, the levels are a minus a plus as I mentioned, and b minus b plus. Information on both factors can be obtained by varying the factors one at a time, keeping the other fixed, as shown in figure 5.7 if you refer to the book. The effect of changing the factors a is given by, so they would be basically combinations where you consider a plus into and b minus and a minus and b minus. So, obviously you are taking keeping a fixed as the higher level and trying to find out the combinations of a plus with all the combinations of the other factors, considering there are only two factors. So, that is why it is given as a plus b minus, and the other combination is a minus and b minus. And if you find out the difference of them and the effect of changing the factors b would basically now be given as, now you keep a minus at this a minus level, or you can consider a at this a plus level, and the values of b as being changed from b plus to b minus or b minus to b plus, whichever way you considered. Because the experiment error is present, it is desirable to take two observations, say at each treatment combinations. That word treatment again is being utilized in a very general sense depending on the experiment, and estimate the effects of the factors using average responses such that you are able to find out the average or the best fit for those combinations. Thus, they would basically be total 6 combinations depending on the 2 combinations of each which you have. If a factorial experiment has been performed and additional treatment conditions of a plus b plus, which is the higher levels for both a plus and a and b are there, would have been taken. Now, using just 4 combinations, 2 estimates of b can be found out, which are, one is a plus b minus minus a minus b minus, which is basically you are keeping b as fixed at a lower level and changing a from a plus to a minus or a minus to a plus, and then find out the difference. And the other combinations would be a plus b plus minus a minus b plus, which means that you have kept b at a higher level, b plus fixed, and basically trying to combine the changes accordingly. Now, you may be thinking why I am taking two stages of combinations only. The reason is very simple, because we considered that a would be at a higher level and lower level. So, what if it becomes that a has 3 levels, a plus, or consider like a1, a2 and a3, where a1 is the higher level, a2 is the middle level and a3 is the lower level. Similarly, you can have combinations of b as b1, b2, b3, where b1 is the higher level, b2 is the middle level and b3 is the lower level, and obviously you will have combinations like this. Listen to me carefully. It will be combinations of a1 with respect to b1, b2, b3, then a2 with the combinations of b1, b2, b3, and the last one would basically be a3 with the combinations of b1, b2, b3. Now, if you look from the other side, it will be b1 with the combinations of a1, a2, a3, b2 with the combinations with a1, a2, a3, and the last one would basically be b3 with the combination of a1, a2, a3, and you can basically expand it and basically had a very simple notion that how these things can be done. So, if you are able to draw it pictorially and find out the calculation, the model can be made much more better in order to do your this calculations in a much more robust way. Robust, again I am using in a much nicer way. Similarly, 2 estimates of b effect can be made. These two estimates, that means for this example we had two effects, because keeping A at two levels you found out two A's, keeping B fixed at two levels you found out B's. So that is why it is said as two levels. These two estimates of each main effect could be averaged to produce average main effects that are just as precise as those from the single factor experiment, but only 4 total observations are required to do this. And we would say that the relative efficiency of the factorial design to a one factor model would be 6 by 4, because in the two factor model, if you found out there were 6 combinations, in the one factor model we found out there were 4 combinations. So the efficiency would be about, or the so called ratio differences or the ratio relationship between them would be 6 by 4, which is 1.5, and obviously it will change depending on what levels of combinations which you take. Generally, this relative efficiency will increase as the numbers of factors are increased. So now it will make sense that when I was mentioning A1 with combinations with B1, B2, B3, or A2 with the combinations of B1, B2, B3, or A3 with the combinations of A1, A3, B1, B2, B3, and similarly the other way around, like B keep fixed, find it out with respect to A1, A2, A3, then go to B2, find out the combination of A1, A2, A3, and basically go to the last level of B which is B3, then find the combinations of A1, A2, A3. So obviously the efficiency would increase because the ratios would increase. Now suppose interaction is present. So in this case this interaction is present, so if the one factor at a time design is indicated, then obviously you will have the combinations of A minus, B plus, and A plus, B minus, because now they are basically affecting each other in a combined effect. So they would give a better response than trying to find out with only A minus, B minus, or A plus and B plus. A logical conclusion would be that A plus, B plus would be even better, because if you combine them, in that case the combinations or interrelationship would be much better. However, if interaction is present, this conclusion may be seriously an error, because in that case you are only taking A minus, B minus, and A plus, B minus. So hence you are eliminating the cross relationship which we have. Cross relationship, I am using the word in this sense: A minus with and B plus, and another is B minus and A plus. Again, only 2 levels combinations. So if I basically have one at a time factor model and at a time experiment, so the combinations are, if you see the graph, along the x axis you are plotting factor A with 2 levels of importance, which is minus and plus, which is A minus and A plus. For the B1 you have basically along the y axis, which is B minus and B plus. Hence the combinations which you have would be A minus, B plus, the combination on the topmost point, and the other one on the bottommost right would be basically A plus and B minus, and the other combinations would be A minus and B minus. So now if we find out the relative efficiency of the factorial design or to a one factor at a time experiment, obviously we find out the efficiency would be 1.5 and so on and so forth. So these values are given. So if you find out for a combinations of a number of factors being 2, then the efficiency is 1.5, which is 6 by 4. If the combination is 3, now the relationship of the factors are 2. If the combinations are 4, then the efficiency is 2.5. If the combination is 5, the efficiency is 3. For 6 combinations it is 3.5, and so on and so. So it will basically go linearly up. So this is for the linear model. I am not considering the non-linear models. So with this we will end the 15th lecture and continue the discussions for the factor models in more details, and slowly expand our ambit of discussions for the ANOVA model, then in the design of experiments, and continue this in more details. Thank you very much for your attention. Have a nice day. Bye.